Welcome to the NPTEL MOOC on Discrete Mathematics. This is the 5th lecture on number theory. So let us begin with a theorem. Let's call it Theorem Phi 1. Let us say GCD of A and M is 1. Then the congruence AX equals B mod M has a solution x1. Moreover, all solutions are given by x equals x1 plus jm, where j is an integer. In other words, there is a solution x1 and every other solution is congruent to x1 modulo m. So that's what the theorem states. So let us prove the theorem. The theorem follows from the generalization of Fermat's theorem. Let us say x1 is a power phi of m minus 1 times b, where phi of m is the totient of m. Then plugging x1 into the congruence, we have the congruence says ax1 is b mod m. Then we have a times a power phi of m minus 1 is congruent to this times b is congruent to b mod m if x1 is indeed a solution. So let us check. We find that a power phi of m times b is indeed a solution, because by the generalization of Fermat's theorem, a power phi of m is 1 mod m, so 1 into b is indeed b mod m. So the congruence is satisfied. So if you plug in x1 as a power phi of m times b1, the congruence holds good. So x1 is indeed a solution of the congruence. Let x equal to x1 plus j into m for some j which is an integer. Plugging this x in, we find that ax is equals ax1 plus a into jm. This is congruent to b mod m, so x is also a solution. So all numbers that are congruent to x1 modulo m are solutions. But are these the only solutions? Suppose y is some solution. If y is a solution, then ay minus ax1 is congruent to b minus b, which is congruent to 0 mod m. Y is a solution, so ay is congruent to b mod m. x1 is a solution, so ax1 is b mod m. Therefore, when you subtract, we have a times y minus x1 is 0 mod m. Or in other words, m divides a times y minus x1. But since a and m are relatively prime, they do not have a common factor. Therefore, it must be that m divides y minus x1, which means y is congruent to x1 modulo m. Or in other words, y is equal to x1 plus jm for some j which is an integer. Therefore, we know that every solution of the congruence is congruent to x1 modulo m, and these are the only solutions. So, let us consider an example. Let us say this is what we want to solve. 353x is 254 mod 400. 353 is a prime, so GCD of 353 400 is 1, and we also know that phi of 400 is 160. We will see a closed form expression for phi later on. So, from that we will be able to calculate phi, but a manual verification will in any case show that phi of 400 is 160. So, 353 power 159, that is phi of 400 minus 1 into 254. As the theorem shows, a power phi of m minus 1 times b equal to x1 is a solution. Therefore, this would be a solution. But how much would this be? 353 power 159 times 254 is what we have to calculate. Of course, mod 400. First, let us calculate 353 power 159. This can be written as 353 times 353 squared power 79. But this modulo 400 can be written as minus 47 into 47 squared power 79. But 47 squared, as you can verify, is 2209. Therefore, 47 squared is 209 modulo 400. So, modulo 400 you can write this as 209 the whole power 79, which is minus 49 into 209 into 209 squared the whole power 39. But then 209 squared is 81 mod 400. Therefore, this is writable in this form. But 81 squared is 161 mod 400. 80 squared is 0 mod 400. 2 into 80 into 1 is 160, plus 1 is 161. So, the equation becomes this: 161 power 19 is what we need to find, all mod 400. So, these are all congruences, which can be further written as, take 161 out, then we have 161 power 18, which is 321 power 9, because 161 squared is 321 mod 400. and then we have 321 power 8. Since 321 squared is 241 mod 400, we can write this as 241 power 4. But 241 we find is which is of course 0 mod 400, so we need not consider it. So we have 480 plus 1, which is 81 again. So this is 81 squared we have already seen is 161. Since 81 squared is congruent to 161, this is congruent to this expression. But we have already seen that 161 squared is congruent to 321. And we know that 321 squared is congruent to 241. And computing 241 into 81, 240 into 80 is 0 mod 400, so we need not count that. So this is 321 once again, which can be written as 200 plus 9 into 320 plus 1 which is minus 47 into 200 plus 320 is a multiple of 400, therefore that doesn't feature in the answer, and 9 into 1 is 9, so we have 9 into 320 plus 200, which comes to 289. So the expression now reduces to minus 47 into 289. 289 is 300 minus 11, that into minus 47 is minus 14100 plus 517. 11 into 47 is 517. 300 into 47 is 14100. But 14100 is minus 100 modulo 400. All this is modulo 400. So we have but 517 is 117 mod 400, so this is 17 mod 400, which is 353 power 159. But what we need to find is 17 into 254. So this (353 power 159) into 254 is 17 into 254 mod 400, which you can verify is 318 mod 400. So 318 is a solution for 353x is 254 mod 400. And we know that all solutions to this congruent are congruent to 318 mod 400. In other words, 318 intersect 0 to 399 is the only solution. in the interval 0 to 399, 318 is the only solution. The other solutions are obtained by moving forward and backward at modulo m. So 718, 1118, 1518 are all solutions. Moving backwards, 318 minus 400 would be minus 82, minus 482, minus 882. Those are also solutions. So there is an infinite number of solutions, but all solutions are congruent to 318 modulo 400. So this is one way of finding solutions for congruences of the form Ax is congruent to B mod m with GCD of Am equal to 1. But it involves finding exponents of this form, which is a long and tedious process. So this is not exactly practical. We will see an easier method later in the lecture. Now let us see another theorem, which is called Wilson's theorem. What Wilson's theorem asserts is this: if P is a prime, then P minus 1 factorial is minus 1 mod P, or in other words, P minus 1 factorial plus 1 is divisible by P. So let us prove this theorem. The proof goes like this. For any A with A varying from 1 to P minus 1, where P is a prime, we assume that P is a prime, then for any A in the range 1 to P minus 1, GCD of AP equal to 1. A and P do not have any common factor. A prime does not have a common factor with any non-negative integer, any positive integer less than that. So Ax equals 1 mod P has exactly one solution. In the interval 0 to P minus 1. This is what we have just seen in theorem 1. Ax equal to 1 mod P has exactly one solution. Here we have taken B as 1 and M as P. So if you consider the integers 1 to P minus 1, in the sequence we have A and the solution x of Ax equal to 1 mod P. So we can think of A and x as being paired off. We want to consider A and x so that Ax equal to 1 mod P. But then could A and x be the same? If A and x are the same, we have A squared equal to 1 mod P. There are two A's which satisfy this. For example, 1 squared is 1 mod P. P minus 1 the whole squared is minus 1 the whole squared mod P, which is 1 mod P. So in this we find that 1 and P minus 1 pair with themselves. That is, 1 into 1 is 1 mod P and P minus 1 into P minus 1 is 1 mod P. But what about the remaining? If you consider the numbers in the range 2 to P minus 2, if A is in this range 2 to P minus 2, then we know that GCD of a minus 1 p is 1, p is a prime. Similarly, GCD of a plus 1 and p is also 1. A plus 1 can be at most p minus 1. Therefore, a minus 1 and a plus 1 are both relatively prime to p. A minus 1 and a plus 1 therefore must be congruent to 1 mod p, which means a squared minus 1 is 1 mod p, or a squared is not congruent to 1 mod p. Therefore, no a within the range 2 to p minus 2 will have this property. A squared will not be 1 mod p. And here we were seeking all the a's so that a squared is 1 mod p. We found that 1 squared is 1 mod p and p minus 1 the whole squared is also 1 mod p. So, 1 and p minus 1 do pair with themselves. But then if you consider the other numbers in the range 2 to p minus 2, we find that these do not pair with themselves. So, they pair with some other. So, any a here will pair with x not equal to a, so that ax equal to 1 mod p. Now, let us consider this product. P minus 1 factorial. Consider the integers in the range 2 to p minus 2. We know that all of them pair with each other. For every a in this range, there is an x within this range that is not equal to a, so that ax equal to 1 mod p. Therefore, the product of all these together is 1 mod p. Therefore, this entire product, which is p minus 1 factorial, can be written as 1 into p minus 1 mod p. Or in other words, p minus 1 factorial is p minus 1 mod p. But p minus 1 is minus 1 mod p. Moving minus 1 to this side, we have p minus 1 factorial plus 1 is 0 mod p, or p divides p minus 1 factorial plus 1, which is what the theorem asserts. Wilson's theorem asserts that p minus 1 factorial is minus 1 mod p. Now, let us talk about solutions of congruences. Suppose f of x is a polynomial with integer coefficients let us say u and v are integers. If f of u is congruent to 0 mod m, and u is congruent to v mod m, you can readily verify that f of v is congruent to 0 mod m. Therefore, when we talk about solutions of the congruence f of x congruent to 0 mod m, we assume that u and v are indistinguishable. They are congruent to each other mod m. So, we essentially assume that they are the same solution. So, we do not count them as separate solutions modulo m. For example, consider x squared minus x plus 4 equal to 0. Its solutions are, this is congruent to 0, mode let us say 10. Its solutions are 3, 8, 13, 18, 23, 28, etc. For example, substituting 3 in this, we have 9 minus 3 plus 4, which is 10. This is 0 mode 10. Substituting 8 here, we have 64 minus 8 plus 4, which is 60, which is again 0 mode 10. So these are all solutions. And you can also verify that if x is a solution, then x plus 10 is also a solution. But then 3, 13, 23, these are all congruent to 3 mode 10. Similarly, 8, 18, 28, these are all congruent to 8 mode 10. Therefore, we do not consider them distinct solutions. We say that we have only 2 solutions in 0 to 9. That is, we have only 2 solutions modulo 10 for this congruence. In general, if S is a complete residue system modulo M, then every u such that f of u is congruent to 0 mod M, and u belongs to S. Such u are what we consider solutions. So the size of this set is the number of solutions modulo M for f of x equal to congruent to 0 modulo M. So we say that this congruence has these many solutions. So within the CRS, we consider all u that satisfy the congruence, and the number of them is the number of solutions that we say the congruence has. When we consider a polynomial of this form, say j is the largest integer, so that aj is not equal to 0, then j is the degree of this polynomial. So let us consider congruences of degree 1. That is a congruence of the form Ax equals b mod M. So by the first theorem of today, we showed that this has a solution. This has a unique solution in 0 to m minus 1, in the interval 0 to m minus 1, if GCD of AM equal to 1. But now let us assume that GCD of AM is small g, which is not equal to 1. So A and M have common factors. Suppose X is a solution of the congruence Ax congruent to b mod M. Then for integer z, for some integer z, Ax equals mz plus b. As Ax is congruent to b modulo m, Ax must be b plus mz for some integer z. Now G is the GCD of A and M, so G divides A and G divides M. Therefore, G must divide B too. In other words, after finding the GCD of A and M, we find that G does not divide B, then there is no solution. Once again, the argument is this: if GCD of AM is G, which is not equal to 1, and the congruence has a solution x, then Ax must be mz plus b for some integer z. Since G divides A and G divides M, G must divide B too. Conversely, if G does not divide B, there can be no solution. So let us assume that G divides B. If G divides B, then Ax congruent to B mod M can be simplified. G is a common factor of A, B and M. In fact, it is the GCD of A and M. So dividing by G, I can rewrite this congruence in this fashion: A by G, X is congruent to B by G mod M by G, by the theorems that we saw in the previous lecture. So it is enough to solve this congruence. To solve this congruence, first let us consider A by G x is 1 mod M by G. We know that GCD of A by G, M by G is 1. They are relatively prime. GCD of A and M is G. So when you divide both A and M by G, then the resultant numbers are relatively prime to each other. GCD of A by G and M by G is 1. So this congruence has exactly one solution. In which interval? 0 to M by G minus 1. In this range, this congruence has exactly one solution. Say x naught is that solution. So x naught is a solution of A by G x congruent to 1 mod M by G. Then let us consider x naught times B by G and substitute this in the original congruence, which is Ax congruent to B, A by G congruent to B by G mod M by G. So we find that A by G times x naught B by G is congruent to since x naught is a solution of A by G, x naught congruent to 1 mod B by G, we find that A by G x naught is 1 mod B by G. So this is B by G mod M by G. Therefore, x naught B by G is a solution of A by G x solution of this congruence. So this is the only solution of that congruence in 0 to M by G minus 1. And every solution to that congruence would be x naught plus t times M by G. Consider all congruences of this form in the interval 0 to M minus 1. They are all solutions of Ax equals B mod M. So Ax equal to B mod M has multiple solutions in the range 0 to m minus 1, and all those solutions can be found this way. That is, when the GCD of A and M is not 1, there are multiple solutions for this congruence in the interval 0 to m minus 1. So let us consider our previous example once again, where we wanted to solve 353x equals 254 mod 400. We know that GCD of 353 and 400 is 1. 353 is in fact a prime. Therefore, 1 can be expressed as a linear combination of 353 and 400 using Euclid's algorithm. We find that 1 is 17 into 353 minus 15 into 400. Taking modulo 400 on both sides, we have that 17 is a solution for 353x equals 1 mod 400. In other words, 17 is the only solution for this congruence in 0 to 399. But what we want is a solution for 353 times x is congruent to 254 mod 400 instead of 1. So if you multiply this solution with 254, which means 17 into 254, which is 4318, which is congruent to 318 mod 400, we find that 318 is a solution for the original congruence. 353 x is 254 modulo 400. So here we have managed to find the solution without resorting to large exponents. Let us consider one more example. Let us say we want to solve this congruence. 15x is congruent to 25 mod 35. So this is of the form Ax equals B mod M, where A and M are not relatively prime. GCD of 15 and 35 is 5. Therefore, it is enough to solve the congruence obtained by dividing this by 5. So A by G is 3. So we have 3x congruent to 5. B by G is 5 mod 7. So let us solve 3x congruent to 5 mod 7. To solve this, first consider 3x is congruent to 1 mod 7. So let us solve this first. GCD of 3 and 7 is 1. Therefore, 1 can be expressed as a linear combination of 3 and 7. So 1 is 7 plus 3 into minus 2. Therefore, minus 2 is a solution for 3x congruent to 1 mod 7. This 7 can be ignored since we are taking mod 7 on both sides. So we have 3 into minus 2 equals 1 mod 7. So minus 2 is a solution for this. But minus 2 is the same as 5 mod 7. Therefore, 5 is the unique solution of 3x is 1 mod 7 in 0 to 6. In the interval 0 to 6, 5 is a unique solution for this congruence. But what we need is a solution not for this congruence, but for 3x is congruent to 5 mod 7. This is what we want to solve. Since 5 is a solution for 3x is congruent to 1 mod 7. 5 into 5, 25 is a solution for 3x is 5 mod 7. But 25 is 4 mod 7. 21 plus 4. Therefore, 4 is a solution for this congruence 3x equal to 5 mod 7. Of course, substituting 4 here, you can readily verify 3 into 4 is 12, which is 5 mod 7. So it is indeed a solution. So we have found a solution for 3x is 5 mod 7. But we want a solution for 15x is 25 mod 35. Since we want a solution mod 35, we would like solutions in the range 0 to 34, both inclusive. We know that 4 is a solution. 4 is the unique solution for 3x is 5 mod 7, but then 4 plus t into 7, where t belongs to z, the set of integers, is also a solution. So any integer of the form 4 plus 7t is a solution. So 4 is a solution, 4 plus 7, 11 is a solution, 11 plus 7, 18 is a solution, 25 is a solution, 32 is a solution. But these are the solutions in 0 to 34. So these are all solutions for 15x is 25 mod 35. So this way we find all solutions within the interval 0 to 34. That is it from the lecture. Hope to see you in the next. Thank you.